Hi, my name is Thales. I'm a senior software engineer at Codeplay Software, and I'm going to present our work towards performance portability of a highly parameterizable TRSM algorithm using SYCL. In this presentation, I'm going to cover the following points. We start with a brief introduction and motivation behind our work. Next, we define the TRSM problem, and we show how to solve it, followed by a gem-based solution to the problem that is suitable to be used in highly parallel devices. I'm going to show the performance evaluation of our implementation of TRSM in SYCL BLAS. And finally, I conclude and present the future work still to be done. TRSM stands for Triangular Solve with Multiple Right-Hand Sides. TRSM is an important operation that is used to solve linear systems efficiently. It is useful when implementing an LU solver because it's used after decomposition into upper and lower matrices to actually solve the system. In this work, we present an implementation of a performance-portable, gem-based TRSM solver that's now available in SYCL BLAS. TRSM is very simple to be solved sequentially, and it can be solved in parallel devices using a gem-based approach that I'm going to show in this presentation. The main motivation behind this work is providing a package with accelerated BLAS routines that can perform well in any device that can run SYCL. SYCL targets many different devices, from CPUs to GPUs and FPGAs, as well as embedded accelerators. Performance portability is a complicated subject, and there are a few approaches that can be taken to achieve it. The library approach means that a library will provide a set of optimized routines that can be used to compose a complex application. The parallel pattern abstraction approach is used by frameworks that exposes the whole program to the compiler so it can optimize the application for the target hardware. In the end, we want to provide a cross-platform performance-portable programming model that can be used in present and future applications without requiring code to be rewritten for new and emerging hardware. For those of you that don't know what SYCL is a single-source, high-level, standard C++ programming model that can target a range of heterogeneous platforms. SYCL has multiple implementations out there, namely Compute CPP from Codeplay Software, DPC++ from Intel, HipSYCL from the University of Heidelberg, and TRSM from Xilinx. SYCL can target a wide range of devices, from supercomputers to embedded platforms. Now, we can define the TRSM problem. As I said, TRSM stands for Triangular Solve with Multiple Right-Hand Sides. The problem we have is that we want to solve for x in one of the following matrix equations. In these equations, OPA could be either A, or it could mean A to be treated as a transpose matrix. The matrix A can be either upper or lower triangular. The matrix A can also have a unit or non-unit diagonal. And A can be on the left side of X or on the right side of X. Alpha in this case is a scalar. It's important to note that for implementation purposes, the solution to this problem must be returned in place of B. So matrix B in this case will be overwritten with the solution to the problem. The multiple right-hand sides comes from the fact that we are solving for multiple columns of X. As you can see, X and B have the same size. How can we solve the TRSM problem sequentially? To solve the TRSM problem sequentially, in this example case where we have A as an upper triangular matrix, it's on the left side of X and has a non-unit diagonal. We can, in this case, start from the bottom, so we calculate x3, and then we can solve each xi from bottom to top. As you can see, the solution to x2 depends on x3. The same is true for x1, which depends on x2, and x0 depends on x1. So, in the end, this is an inherently sequential algorithm. This algorithm is called the retrosubstitution algorithm. However, this algorithm, as is not suitable for highly parallel devices, such as GPUs, since the solution to each row I depends on the solution to all rows below it. One way to parallelize this operation is to convert the problem to be solved by a gem call. We can multiply the input equation. We can multiply both sides of the input equation by the inverse of matrix A, which yields this expression here. This expression can be calculated by a single call to gem. This works, but it's not very efficient. Inverting a matrix has complexity in the order of solving a linear system, so this leads to solving the TRSM problem twice. Again, the goal is to leverage a highly optimized gem operation that is already available and performs well. How can we turn this problem into an efficient gem-based TRSM solver? What we can do is we can decompose the input matrices of our problem using blocks of fixed size. As an example, if we decompose our problem into blocks like these ones, shown in the diagram, we can arrange the equations like the following. And then we can solve each x again from bottom to top, like the following. Note that this is still a form of sequential retrosubstitution, and the solution for x0, for example, depends on the solution for x1, which in turn depends on the solution to x2. However, arranging the problem like this allows us to leverage an existing optimized gem to solve each x. Note that the data in this case doesn't need to leave the device's memory while the problem is being solved. This arrangement still requires us to calculate the inversion of the diagonal blocks of the input matrix A. The difference now is that each diagonal block can be inverted independently of the others, and this nicely maps to GPU workgroups, where each workgroup can invert one diagonal block. Note that each diagonal block is also a triangular matrix, where half of the elements in each block is 0. The result of this operation is a buffer containing only the inverted diagonal blocks. Then, this buffer is used to perform a series of gem calls that are going to solve the TRSM problem. In this diagram, we show the data access pattern for each thread in a workgroup performing the diagonal block inversion. Each element in orange requires access to the elements shown in yellow. And the threads in the workgroup, they work from bottom to top. Because again, calculating an inversion is like solving a linear system of equations. When you write an application, the SYCL runtime will implicitly build a dependency graph based on each kernel dependencies and will automatically schedule them in the right order. This frees the programmer from having to think about dependencies between kernels. The diagrams in these slides show the dependencies between each kernel launch in our example TRSM problem. We start by running the diagonal blocks inversion kernel, followed by two gem calls to solve each block xi. The SYCL runtime takes care of launching the kernels in the right order, as this is done automatically by the runtime. The gem algorithm implemented in SYCL Blast uses a tile-based approach to compute its results. This efficient gem implementation is a key factor in the performance of our TRSM implementation. Usually, developers spent a long time optimizing the gem implementation in BLAS libraries. So by leveraging this gem implementation, we can achieve very good results. In this slide, we show the performance evaluation of our TRSM solution. We selected 3 GPU devices that represent hardware used in different scenarios. The Intel Ultra HD 630 is an iGPU available in the Intel Core i7 8700. The AMD Radeon RX 460 is a discrete desktop graphics card, and the ARM Mali G71 is an example of an embedded GPU, in this case available in a high-key development board. We compare our implementation with 2 other portable BLAS libraries, CLBLAS and CLBLAST. CLBLAST is a highly optimized BLAS library provided by AMD, and CLBLAST is a BLAS library that can be tuned to specific problem sizes. Both libraries are written on top of OpenCL, and were selected so direct comparisons between the TRSM implementations could be performed. The graphs show the gigaflop performance of the 3 libraries running in our selected GPU devices. For the Intel GPU, SYCLBLAST has good performance, comparing to the others except for the smallest problem. On the AMD GPU, CLBLAST beats SYCLBLAST for square problems, but loses significantly for rectangular, large TRSM problems. In the ARM GPU device, SYCLBLAST achieved excellent performance when compared to the other libraries. Note that ARM doesn't provide a TRSM implementation specialized for the Mali G71 device, since the ARM Compute library doesn't have the TRSM routine available for use. In the AMD GPU device, we noticed that CLBLAST performs very well for square problems up to the size of 5K by 5K, but its performance drops significantly after that. For the ARM GPU, the gem routine available in SYCLBLAST is extremely optimized for the hardware. So, the gem available in SYCLBLAST automatically selects which kernel performs best based on the size of the TRSM problem that we are trying to solve. The same happens in the Intel GPU device. The gem kernel available in SYCLBLAST is highly optimized for this device. So by leveraging a highly optimized gem routine, we can implement TRSM and have a performant TRSM available in this device as well. As discussed previously, the block size used in our TRSM implementation is fixed, so we need to figure out what is the best block size to use. In these graphs, each column represents a TRSM problem of common power of 2 sizes. It ranges from 64 up to 4096. And the numbers below each graph are the block size used to solve the problem. So for example, in the first line, we have the AMD Radeon RX 460 device. And this shows the TRSM performance, our TRSM performance solving problems of the size displayed here. The bigger the block, the more time is spent doing inversion, because blocks are bigger and we need to invert each block in the diagonal blocks inversion kernel. For small matrices, we end up inverting almost the whole matrix. And as I discussed before, this is like solving the problem twice, so not very good. As you can see, for the AMD device, using a block size of 90 and solving a problem of 64 by 64, almost 100% of the time is spent doing the diagonal blocks inversion. In these graphs, the yellow bar represents the relative time spent calculating the diagonal blocks inversion, and the blue bars is the time spent doing the gem calls. This approach, however, pays off for larger matrices. As we can see, for example, in the Armali G71 device, when we get block sizes of 128 by 128, we get almost no time. We spend almost no time doing blocks inversions when the size is 4096 by 4096, and we spend the majority of the time doing the optimized gem calls to solve the problem. And we can see this happening across the board. At the moment, the block size is limited by the amount of shared memory of a device, so that we don't have results for a block size of 128 by 128 on the AMD GPU, since its workgroup shared memory size can't hold a block of floats of that size. To conclude, in this work, we presented a parameterizable TRSM implementation now available in SYCL BLAS. This means that we have taken a step towards performance portability of all BLAS operations in SYCL BLAS, which is a key component in modern HPC and embedded environments. We show competitive performance against optimized vendor-specified libraries, CL BLAS and CL BLAST. For future work, we need to add support for diagonal blocks of arbitrary size. We can also vectorize the block inversion algorithm and provide a version that doesn't use local memory for devices like the Armali, where using shared memory doesn't bring benefits since the device doesn't have one. We need to further improve the performance. We can further improve the performance by using batch gem calls to accelerate the solver, and we also need to evaluate the performance in CPU devices. Thanks for listening.